It's a pleasure to be here to present to you some of the current developments of an ASME standard for measurement of key indent characteristics. My name is Dr. Terry Beck. I'm with the Department of Mechanical and Nuclear Engineering at Kansas State University. My colleagues are listed here, in particular Bob Peterman and John Wu, and also John Bloomfield, who is an engineer that's been involved in this project quite extensively. There were also a number of other students involved, grad students in particular, and at least give them some credit here. They contributed a lot to the project. This project comes out of a couple of projects funded by the Federal Railroad Administration, one involving determining the variables that influence transfer length, and the other developing qualification tests to ensure that the concrete materials combined with the indented wire make up a viable crosstie or tie material. I'd like to acknowledge the sponsors, primarily the FRA associated with this project, and there were a number of other contributors as well in industry. Quick outline, I'm going to give you some background on the prestressing wire indent characteristics, some of the known geometrical features that we're familiar with, look at the basis for a new measurement standard really, and then show you some of the developments towards a new standard for indent measurements. And then we'll show some comparison of manual and automated results of the scanning of the indent features, and then talk about conclusions and future developments. First, some background about the prestressing wire. As many of you are probably familiar with, the prestressing wire is formed, the indents are formed in a roller setup like you see here, and the rollers provide or produce an indent in the wire as it's drawn through. There are two key things about the indents that we need to be familiar with. One, indents influence the transfer length, the distance required to fully transfer the prestressing force, and that can be a major influence if that transfer length is less than the distance to the rail seat, because the load-bearing capability will be reduced. They also have a significant influence on splitting and splitting propensity, and we've identified a number of the features that characterize splitting regarding these indents. Let's look at some of the known indented wire geometrical characteristics. This is kind of a list. I mean, some of these you're familiar with, I'm sure. Indent depth, volume, sidewall angles, and so on. There are a number of them mentioned in the two main standards, ASTM A881 and ISO 16120. We'll talk a little bit more about that later in the talk here. This is a schematic of 3D indent geometrical features, the most general ones, including indent volume and depth and area and so on. There's a number of them listed here, about 9 in fact. We can also look at 2D characteristics, geometrical features, and in fact slice down the center of a given indent, and you can get a lot of useful information, primarily from the point of view of determining transfer length, but the splitting propensity is a little more complex. But nonetheless, we investigated 2D characteristics here as well. A new parameter that my colleague Bob Peterman proposed recently is the byte per length. We're investigating this as a precursor to the splitting characteristics, and it is kind of a measure of the projected area of the indent divided by the pitch distance. And down below you see a couple of the typical kinds of indents. The crisper ones, European T2 style, and then the European T4 style, which is more tapered indent characteristic, like you see in the figure here. We've measured both. Okay, let's look at a basis for the indent measurements. We really never had the capability before an automated system was developed to do justice to the measurements. We didn't have high resolution measurement capability. We couldn't measure large statistical samples to get an idea of the statistical variation. We couldn't measure significant lengths of wire indents, like hundreds of indents at a time. We're pretty limited to manual type measurements. And so also the key features that affected transfer length and cracking or splitting weren't known. And that's really what led to the current developments. This is a microscope image of some of the features, visual features on wires that we have tested. You can notice that you can also see damaged indents. We don't know exactly what the influence of that damage will be. We have developed an automated scanning system. This is a schematic of it. It takes slices with a light scanner, laser light sheet generator really, and from those scans we can reproduce to a very high resolution the shape of an indent. This is a picture of the automated scanning system with it works on a lathe to traverse the scanning system along the length of the wire, and then the result is processed in and controlled in a LabVIEW code. We can measure up to about 26-inch length of scan wire. This is a small segment of that, so we can cover all 3 rows and get up to several hundred indents for a given overall scan of wire. So this capability had never before been possible. For a given scan line, we can reduce it then to what we call an elemental trapezoidal shape, like you see here. And from that shape, we can process all of the key characteristics of the basic indent shapes. And this could be done also manually. This is just a snapshot of some of the measurements that were made with our automated system of the left and right hand sidewall angles. And you can see the statistical distribution that's shown for the 2 different orientations, the left and right hand side. We have enough capability that we can get large statistical samples up to 100 or more and get a good histogram distribution. This is a shot of the indent depth. Again, you see the variation of the indent depth for different rows, 1, 2, and 3. And the typical average depth is about 160 microns. We've identified the key parameters that affect transfer length, and they're listed here, like volume and sidewall angle and release strength and so on. And we can put that together in a correlation plot, linear correlation of the variables. And what you see here is the result of the correlation. It has a coefficient of determination of about pretty close to 0.9, 0.88 anyway, indicating that there's a very strong correlation of the geometrical indent parameters and the transfer length. Likewise, we've identified the cracking propensity by doing extensive tests on prisms with various amounts of cover and different prestressing wires. And we've developed a correlation for those similar. This is the crack length correlation with variables of indent shape, including volume, depth, sidewall area, sidewall angle, and the amount of cover, which is a strong contributor. Again, we get a coefficient of determination of about 0.8 in this case, indicating a large amount of correlation. So we pretty much know the important influences, at least to the best extent currently available. And we're in a position now to develop a new standard for making indent measurements. The standard is to address the current limitations of the existing standards, include the key geometrical features, and we also want to provide the capability of doing both manual and automated measurements, and recognize some of the detailed characteristics from row to row and so on. The scope of the standard is kind of indicated here. We have a focus on prestressing steel wire with either chevron indents or elliptical indents. These both have well-defined flat basin geometries, and we presume, at least in our scanning system, that we have 3 uniformly spaced rows of indents, although that isn't a critical thing. The full 3D scanning feature extraction then is going to consist of taking parallel scans or traverses, if it's manual, for each row, covering at least 3 indent rows, or all 3 indent rows, I'm sorry, with at least 3 parallel scans, and including a centerline traverse. The resolution of the measurements needs to be pretty significant because the Depth, for example, is on the order of 160 microns. So minimum depth resolution on the order of 5 to 10 microns is required. Axial position resolutions on the order of 20 to 25 microns, and lateral position, similar resolution. And we need to be able to do this with both stylus as well as non-contact, our optical measurements. Again, this is a basic list of the key measurements that are important. And so I'm going to kind of go through and show you basically how we get those measurements from the point of view of a standard. The idea is to set up a standard that everybody can measure, and it's based on this trapezoidal geometry that we get for a given slice. And it's shown down here at the bottom. So we need a minimum of about 9 measurements to determine the parameters that I've described, the geometrical parameters. And points 1, 2, 3, and so on, these can all be measured with either radial or axial type measurements. Here's an algorithm to generate, for example, the indent depth, the average indent depth. We take a slice, we determine the depth from points 1, 3, 6, and 9, and then we get an average depth by taking multiple scans and simply averaging. And to determine the indent pitch, that's pretty straightforward. We just take the distance between typical points 2 and 8. Again, you could do this multiple times if you had more indents, but that's for a single indent based on that 9-point determination process. Indent width is a little more complicated, but it still can be resolved quite nicely like you see here. And we can also define the positioning of at least 3 scan lines in between. So that will give us the ability to do averaging of the various parameters such as depth. The basin and plateau length is another variable. This one doesn't show up directly in the standard, but it still is indirectly involved in such things as, for example, the indent area and volume here. So we can find the profile area from multiple profile areas. We average those, multiply by the width, and we can get the an estimate of the volume. Sidewall angles, we can measure either the left or the right-handed. Left and right is kind of arbitrary here, but or we can define an effective average, which we're still investigating that. But these angles are subject to a lot more uncertainty because the dimensions are quite small, the distances are small. And likewise, the sidewall lengths are also a little more difficult to measure. But again, this is a standard algorithm, and we're going to look at some comparisons. And in particular, comparing the manual with the automated scanning, that gives us a way of justifying the legitimacy of these algorithms, because nobody's ever come up with a general algorithm for making such measurements. We have a very detailed algorithm in our automated scanning system, but the idea is to make an algorithm or algorithms like the ones I just presented that are usable by anybody for people that have a scanning system of sorts like this, or even doing manual type measurements. Here's just a shot of multiple line scans. From each one of these line scans, we get discrete points, and from those points, from outside edge, we can get the width measurements as well. From those, we can all determine these trapezoidal elements. And from the trapezoidal elements, we can get all the geometrical parameters that we described, or that I described earlier, using the simple algorithm from those 9 points. This is a comparison of the manual measurements to the full scan results. And on the left column here, you see the manual measurements of width, pitch, volume, and so on, depth. The width and pitch are subject to very small uncertainty or error, on the order of 1 to 2%. The volume and the depth and so on are on the order of 5% or so uncertainty or error, I guess, in terms of the way we did this. The full scan result here takes into account all of the general algorithms that were developed in our scanning system, not just the discrete points that I described in the simple manual algorithm. And then down here we have a comparison of the angle, the sidewall angles. And sidewall angles have the largest uncertainty, but still it's on the order of 15% or 16%, so it's still pretty good. as far as its error as well. Now, what we've done here very quickly is just kind of proposed a new standard. This standard is currently still under development. It has the advantage, though, of identifying the key features. It includes the key features that are correlated to tie performance, namely transfer length and splitting propensity. And it is based on this idea of the scanning and the trapezoidal element that can be used in processing algorithms, real simple algorithms, for determining all of these geometrical parameters either manually or in an automated fashion. And it's this comparison that really provides the justification and the verification of the algorithms that we're proposing. Our plan is to put this together into a formal ASTM standard template and have this ready by the end of the summer. And hopefully by the end of the year, then we'd have things submitted for review. I'd be glad at this point to answer any questions that you have, or you can contact me later as well. Thank you very much for your attention.